Right. So it was only 90 seconds after takeoff, Euroflight 178 found itself in a cornfield. What had happened? Well, a flock of birds just brought a state-of-the-art aircraft down. Yet if you look at this picture, there isn't really a sense of chaotic event that just happened. It just looks like a plane is just like chilling in a cornfield. And indeed, actually, this event wasn't as tragic as it could have been. Everybody survived this ordeal. And for this reason, this event was dubbed the miracle in the cornfield. The pilots were praised for their airmanship and saving everyone's life. That was a beautiful day. But was it actually a miracle? As it turned out, the leaked accident investigation revealed that no, it wasn't really a miracle. In fact, as the birds tracked the plane, the pilots were so disoriented. They did everything that they could do wrong, and they actually tried to bring down this plane because it was just so chaotic. Luckily, the plane's fantastic automation just basically kept everyone alive. And for this reason, you find on this video that I was showing before that comments like this or like this. So in short, the plane saved itself and everyone from a bad outcome. Okay, so if you're wondering if this is still a talk about cryptography, yes, and I will get to that soon. But beyond cryptography, the message that I want to also get out of this is the power of automations in securing systems. In particular, I believe automation has the power of systematizing knowledge and security checks and security controls. It allows to make incremental improvements safely and reliably. And all of that can be done also thoroughly once things are automated. Cool. So let me just quickly talk about myself. I'm a cryptography analyst at Trail of Bets. I'm originally from the DR Congo. And in my free time, I'm a hobbyist musician, dancer, and concierge for some reason. That's enough about me. So let's talk about deployment of cryptographic applications in the wild. How can we assess them? How are they deployed? Well, the rule of cryptography in the wild is basically don't roll your own, right? That's the end of my talk. Thanks for coming. If you do it well, you can even sell merch with stickers about not rolling cryptography. Obviously, the truth is that that's not the end of the story. Things are a bit more complicated. And the point I want to make here is that don't roll your own, although it's a good advice, it sometimes creates a mental model that is detrimental to how cryptography can be deployed in practice and have sometimes negative consequences. In particular, sometimes people think about don't roll your own as, my application, as long as it has a list of blessed primitives and very good implementation of them, I'm fine. You're good, right? Well, in reality, things are not as simple. So there are three things that don't roll your own misses. First of all, a cryptographic primitive such as AES is really just a security contract, which means it defines assumptions under which you get a certain security property. And these are very precise notions, right? For example, well-implemented AES in counter mode provides you indistinguishability under chosen plaintext attacks. This is very precise, and doesn't necessarily cover anything else that you may sort of intuitively expect from an encryption scheme. And besides that, in actual applications, cryptography doesn't live in a vacuum. It actually is part of an application, and this application has certain business needs. No one is trying to build INDCPA things. People are building end-to-end encrypted systems, right? And the type of functionalities that you may want to provide may end up affording potentially malicious users more power that actually goes outside of a INDCPA model, for example. And the third thing is compositions. I guess this is really just like talking to the choir here, but especially for people who use cryptography on a daily basis, you may have ideal cryptographic primitives, but the way you combine them might not necessarily combine into the ideal thing that you want it to be. And this is not just theoretical. I want to highlight a couple of real-world examples that show this problem. You may have seen recently there were some research about breaking security of Threema. There are a few attacks that were shown, and I'm not going into the details, but the key point here is that basically Threema was using all of the right primitives. It just turns out that it didn't combine into an end-to-end encrypted secure messaging. The other example is BridgeFi. Again, this is even weirder because BridgeFi actually was using libsignal underneath, and yet BridgeFi was broken again. Libsignal is sort of what is implementing the signal protocol, which is the state-of-the-art messaging protocol, and yet an application uses signal in a way that's broken. And I really encourage you to have a look at this paper from Patterson and Albrecht. These works actually that I was mentioning before are from a line of work that they've been doing on breaking cryptography in the wild, and they have some very nice reflections on how cryptography in the wild is executed. Good. So if you buy a bit like the narrative that I've been giving so far, don't worry, it won't basically resemble a tutorial on how to draw an owl. You have AES, you have ECDSA, the two circles. Now go ahead and draw the owl. Obviously, that doesn't work. So what's the way out? I claim, just like anything, as long as you're combining cryptographic primitives in some way to achieve some functionalities, you still require to have a certain amount of rigorous analysis of the overall system. This includes, so from here my slide actually is very not readable, but I hope you're sort of able to see. So this includes sort of security proofs and pen testing and code review and design reviews, but also understanding threat models, because, if you're building an end-to-end system, you shouldn't be surprised that someone tries to break it from the standpoint of a server. And I believe this is where automated verification plays an important role because it allows to sort of capture all these things in a very systematic manner. And also when used in the early phase of deployment, it will then allow to catch some low-hanging fruits, things that, for example, should really not exist in 2024. Right. So I've been talking about rigorous analysis, but what do I mean by that? And for people who are not familiar, I would just want to try and go briefly through what exactly that means and how hopefully you may also be motivated to try and use that in your own work. So when you talk about cryptographic analysis, there's basically two sort of approaches, known as a computational model and a symbolic model. This is a table that might look overwhelming, but I'm going to sort of walk you through it. Basically, the computational model is sort of the classical way of analyzing cryptographic primitives. Here we think of primitives are sort of functions. You think of AES, it's something that takes some inputs, which are like bit strings, and give you out some other bit strings. And adversaries and users are basically Turing machines. They can do any kind of computation they want as long as they're able to do it efficiently or fast enough. On the other hand, the symbolic model mostly sort of considers perfect primitives. Things are basically black boxes. For example, here that's an example of how you define security of an encryption scheme, meaning that only having the right key allows you to decrypt a ciphertext, which is a much weaker security notion than actually what you do have in the computational model. And on the other hand, the adversary in the symbolic model is also fairly limited. A symbolic model will define a certain number of primitives and terms, and the attacker can only sort of manipulate the terms that are defined by the model, which is obviously limited and more limited than a sort of general purpose Turing machine that can just do any kind of computation that they want. And for this reason, the computational model tends to be sort of more realistic in some sense, but there are still some limitations. It allows us to capture attackers that can do sort of different kind of things, whereas the symbolic model is fairly limited, but this comes with a certain advantage that I'll describe later. So when it comes to actually using these models to analyze some protocols that you want to analyze, the computational model is usually super tedious to do. You have to write sort of pen and paper proofs typically. I guess the next talk will also sort of be going a bit into some of those considerations. And the way you do it is by defining a game, a so-called security game, that captures interaction between an adversary and a challenger. And the game sort of expresses the conditions under which a certain security property is guaranteed. On the other hand, when using the symbolic model, things are usually mostly automated. So this is great because there's a lot of tooling that allows you to basically just do your analysis simply as soon as you have your model. And the great thing about the symbolic model is actually it provides with attacks. So if you model a protocol and something is wrong, it will show you there's an attack somewhere. And as I said, in terms of tooling, computational is fairly limited in terms of tooling, whereas there are a few nice tools in the symbolic model that I will now describe briefly. So the two main tools for symbolic analysis are Proverif and Tamarin. I'm not going to go into the details, but basically Proverif is one of the mostly used tools to analyze protocols. It uses the so-called applied pi calculus to model protocols and attacker capabilities. But it's been used to model a few interesting things, including Signal, so the PQXDH extension that you may have heard of. It's been used for TLS 1.3, WireGuard, and so on. The second tool is Tamarin. This sort of uses a different mechanism. It models protocols via state transitions, and the state is represented as a multiset of facts. You don't need to care about this. You can if you want. However, it's also been used for a few interesting protocols. So, for example, Apple's PQ3 post-quantum transition of iMessage. It's also been used for TLS 1.3. It's been used for WireGuard and other type of tools. A few things that these things have in common is that they allow to define custom cryptographic primitives via an equational theory. So you can sort of define equations, just like as I showed with your symmetric encryption, that capture your scheme. And they also typically allow for unbounded sessions, and they allow to prove a few security properties like secrecy, correspondence, and authentication. Right. However, for my demonstration here, or as a running example, I'll be using another tool that's known as VerifBar. It's a tool that is far more limited than the ones that I've shown before. But the great thing about VerifBar is it's very beginner friendly. It's built in a way that is sort of opinionated, and you can't really extend it with functionalities and other things. And the idea is that it's sort of geared toward developers, and in a way that they really won't be misusing the tool, and they can start modeling their protocols and their applications VerifBar and hopefully get some result out of it quickly. Cool. So how does VerifBar work? So this is a 3-minute tutorial. Please have a look later. But it's basically, in VerifBar, we first of all can specify attackers that can be either passive or active. Users in VerifBar are specified as principals. You sort of, on the left side there, that's sort of how you'd specify a VerifBar model. A user can sort of do any kind of computation like generating random Diffie-Hellman shares and so on. And VerifBar also has a message sending capability, and message can be sent either unauthenticated, so the attacker can just do whatever they want with them, or messages can be guarded, meaning that there is no modification allowed on these messages. VerifBar also includes support for a few primitives that goes from hashing, signing, or even secret sharing. And importantly, VerifBar also has things called checked primitives. These are primitives that capture sort of primitives that compute some sort of a check and may fail if the check doesn't pass. This includes, for example, when you're decrypting something with an AED and authentication tag doesn't match, for example. In this case, VerifBar will stop the execution. Good. So this is a simple protocol specification in VerifPal. Basically, this is just modeling an authenticated Diffie-Hellman key exchange where Alice and Bob establish a shared secret key via the Diffie-Hellman protocol, and Bob sends ciphertext later back to Alice. I take this example, and it's from the VerifPal manual, and again shows you some of the limitations, I guess, from the tool as well that's I think is not maintained anymore, but you see the sort of the protocol diagram and the code actually they don't exactly match. There's a little bit more happening in the code than the specification, but the idea is basically the same. Good. And now let's say you've modeled this protocol and you want to sort of find things, you want to sort of question VerifPal about the properties of this protocol. You do so via the so-called queries, where you can, for example, ask for confidentiality, authentication. In this case, we're trying to ask whether the ciphertext is confidential, which is, I guess, not a sensible question, but why not? And also asking, for example, for the confidentiality of the message that Bob did send encrypted with an AED. And once you have all this, you can just put it in a VerifPal file, and to verify it, just run VerifPal verify the file, and it will give you some result. In this case, obviously, under active attacker, nothing is secure. Again, that's a good reminder. Don't use unauthenticated Diffie-Hellman if you're trying to create secure communications. And VerifPal is really nice. It thanks you for using it, so yeah, give it a try. Now, as I said, I also want to sort of inspire you a bit to try VerifPal and to really have the courage to go out there and just let me try. So for this, I want to take another example. And the example I'll be looking at here is the 3DH protocol. It's not exactly, there are many specifications. It's just my variant, I guess. And it's a very nice and elegant protocol that allows you to actually establish secure channel in an authenticated manner. The way it works, briefly, is that we have Alice and Bob, they have long-term Diffie-Hellman keys, and to establish a session key, they basically send to each other an ephemeral Diffie-Hellman share and their long-term share. And then they do all kind of Diffie-Hellman between the ephemerals and long-term, which then is passed into the KDF, so that's the IKM or input key material parameter there. And also as context, they pass basically all of the communications to bind the session key to the communication. And this is a so-called implicitly authenticated key exchange, meaning that at the end of this protocol, Alice actually isn't sure. She actually has been talking to Alice, but she's guaranteed of one thing. If someone derives the same key, that'll be Bob. And this is how authentication is captured. So now imagine you have to audit some cryptographic scheme, and someone said, hey, you know what, we've seen that 3DH is a good protocol, we wanted to build on that, and add an additional feature, which is protecting identities. And the way they do this is, you know, you start like the 3DH, you send some ephemeral Diffie-Hellman keys, but before sending the long-term keys, you actually encrypt them under a key that's generated from the ephemeral keys. And furthermore, you also simplify a little bit the key derivation there, you know, because the long-term are hidden, the attacker doesn't know them and whatnot, so you can keep it simple. This is a protocol that's broken. I think crypto people have seen already why it's broken, but if you're not a crypto person and you are tasked with trying this, I really encourage you to go ahead and give it a try. Good. I think described that. I just want to now quickly just highlight a few use cases of formal verification in practice, and how it's been used to actually enable new protocols to be rolled out quickly and reliably. So my first use case will be OCAM. That's a protocol that we reviewed as part of my work. So what's OCAM? It's a set of protocols and managed infrastructure to allow secure communication in diverse environments. The way it works is that it's building upon the well-known noise protocol. And for authentication, it relies on what they call OCAM identities, which is basically a concept that captures a binding between an entity and a long-term key, and also its change across time, kind of like a blockchain somehow. And how did we go about verifying this, besides sort of auditing normally and then kind of just staring at a protocol and trying to find problems? We provided a verifiable model to the OCaml team. Why was that the case? Well, verifiable was basically like the first tool that we started experimenting with. And the value for us was that we could provide a model that was simple enough so that once it was defined, a customer could take it and also continue using that as long as they were sort of iterating upon the protocol. For sort of more fancy cryptographic properties, we use a tool called Cryptographic. That was to sort of get some deeper understanding around the sort of guarantees of the signatures that are used in the OCaml identity design. By the way, Cryptographic is the tool that I didn't mention, but it's actually a tool that is used for computational analysis. It also allows you to sort of have machine-checked computational analysis, but it's far less limited. It's far more limited than symbolic counterparts, and typically you still have to guide it in terms of proofs. The next example is the PQXTH. So as you've seen, Signal has released updates to its protocol that allows it to be hedged against store now, decrypt later attacks, which basically target sort of capture a quantum attacker that may be capturing your Signal messaging now and hopefully wait for a quantum computer to be able to break your, to start reading your messages later. And for this, they basically took the original X3DH protocol and combined it with a post-quantum CAM. And yeah, exactly. Now you get sort of a post-quantum handshake for Signal. This is not work that we did. This is work that was done by a team at Crispin. What did they do? So they provided a proof model that allowed them to prove several key exchange properties, like authentication, but also actual security against store now, decrypt later attacks. And also, as they were doing this work, they actually found several attacks in Signal, and which allowed to actually improve the specification, and the latest specification that was published actually got rid of those issues. I hope you can see. Yep. And the other case that I've mentioned before is sorry. Yep. Yeah, so let me jump to this. The other use case is Apple's PQ3, again, another sort of post-quantum addition to a messaging application, in this case iMessage. There was a tool that provided a tamarin model that again proved several authenticated key exchange properties. And in this case, actually, PQ3 is a ratcheted key exchange, meaning that there are still sort of exchange of ephemeral sort of secrets at times, which allows PQ3 to still have post-compromise security. That is in contrast to PQXTH, which only has sort of post-quantum sort of handshake security. And for PQ3, there was also a computational analysis that was actually done. That was a fully pen and paper proof, which allowed to then prove some more fine-grained security guarantees of PQ3. And last example I want to highlight is HEDOC. HEDOC is, you can think of it as a lightweight alternative to TLS 1.3. It has been standardized recently by the IETF. And for HEDOC, so that's a mistake there. There was actually a proof model that was done. And what was very impressive about this is that the draft was being updated, and the proof team was also able to keep up quickly with the changes and be able to validate or sort of say that some of the changes didn't improve security and whatnot. And besides that, there are also lots of other pen and paper computational proofs, one of which we also contributed in work that was done as part of my master thesis. But again, being able to have tools that sort of automate things was such a great asset to have. So I suppose here the message for me is that tool-based formal verification is increasingly practical. And I really want to encourage us to really, if you sort of dealing with cryptographic schemes, if you assessing some kind of cryptographic related application, please give them a try. And I think they provide lots of benefits. Cool. All right, so I seem to have been sort of selling a bit of a dream, but there are some limitations, and I want to address them. The first thing is that I'm talking about proofs and cryptographic proofs and formal analysis and whatnot. While a proof, is still done as part of a model, and the proof will only be as good as the model. If your model is modeling nothing relevant, the proof won't also be that meaningful. And this is a quote from a gentleman that seemed to be looking, I don't know, sort of happy, I guess. So more concretely, what do I mean by that? So a proof really only means that there is a theorem. But you have to really understand sort of when you're establishing a theorem, there's sort of hypothesis and whatever conclusion you get out of it. So it's important to be able to make sure that the assumptions of your theorem are clear. As I showed before, as I was talking before, if you have an application that's trying to build a cloud messaging and whatever functionality you build on top of it start going outside of the attacker model, of the scheme, of the primitive that you're using, you may not necessarily have any sort of security guarantee out of that. The next thing is that typically with sort of this kind of tooling, something that one does is typically to start exploring attacker models, right? So what's the furthest I can do? What's the furthest I can allow my attacker to do? And this is great. It's nice. But it's also good to keep in mind the sort of wealth of knowledge that there's in the community about the type of threats that one should really be considering for their applications. So, for example, if someone is building a cloud sort of, cloud backup system or something, as you're exploring this model, you should also keep in mind the sort of real-world attacks that have been done on cloud messaging and the type of attackers model that you should actually be keeping in mind. And this may not necessarily be something that you may come upon yourself if you're just exploring things. And also, as I said before, especially in the symbolic type analysis, you're always sort of working with idealized sort of primitives in some sense. And when it comes to real-world implementations, your implementation may, because of how they're implemented, they may actually start deviating from your expectations or sort of the assumptions that you're making in the model. And this is not only limited to symbolic analysis. It also goes for computational model. I said computational is more realistic, but again, it's still a model that has to some extent, abstract the world and keep to the sort of cryptographic core and the very sort of relevant things. Yet in the real world, the way things will work might deviate from the assumptions. So I'm not sort of claiming that once you've run Verifpal, you're good, no need for pen testing, no need for code review, no need for anything, right? This is still sort of a layer, let's say, in the Swiss cheese model of security. I don't know if this is a term that's used typically in security, but I guess aviation people use Swiss cheese for some reason. And the other aspect is as well that using such tooling is in doesn't come for free. It comes with a cost. And there are sort of two that I want to mention here. First of all, learning curve, right? Verifile seems to be like a very nice and easy tool to use, AAD described here and send message there and guarded, not guarded. You have your queries. But it still takes time to use, to get used to it. And also, furthermore, once you want to actually start getting additional properties by using a more advanced tool like ProVerif or Tamarin, there will be more learning to be done. But I think the good news here is that, just like anything, there's always a bit of learning needed. And the more you do it, the better you get at it. And I believe for sort of security community like this one, right, we keep on adapting and sort of trying to use the new tools that are out there as long as they sort of provide more value for this. So I would say this is, for me, sort of not a deal breaker. But yeah. It's still consideration to keep in mind, for sure. And particularly for people who are assessing systems, security systems, if you're auditing or doing pen testing, obviously you have a limited amount of time, and if you're sort of looking at the cryptographic segment of that application, you have to make a decision whether using a tool is what you want to do or not, because you have limited amount of time. Again, here I claim, with each improvement and with each learning that you do, you get more effective at the tool, and I believe you will still be getting more value out of the tool. So, in terms of limitations, so I'm not selling a magic wand. That's I hope this is still clear. We'll still need to be doing code reviews. We'll still need to be doing pen testing. But I think introducing something like formal verification, hopefully automated formal verification, allows us to have stronger guarantees and be more confident about the protocols that we're rolling out. Good. So with that said, I want to come back a little bit to the title. That felt a bit like, I don't know, somewhat unrelated to what I was talking about, but let me sort of try and describe a bit the mindset behind it. Start them early. Why start them early? Because I believe including formal verification early in the design process allows to really put applications in strong foundations. They allow to get rid of low-hanging fruit, which then focuses later efforts on sort of much more valuable tasks, right? If you're sort of working with auditors as a developer, for example, it's great already if whatever you present them to work is something that has been sort of gotten rid of issues that, one should have gotten rid of, hopefully, like in an automated manner. And keep on keeping on. Well, that's because, security is a process. Nothing is perfect. I'm not presenting a perfect tool, not a magic wand, but I believe as a community, we should be, we have a responsibility to start demanding higher and higher standards from the primitives that's being used and the type of deployment that we're seeing in practice. So with that said, this again sort of a reminder of some of the tools that are out there that enable automated verification of cryptographic protocols. And there's my email there if you have any question. So this was a fairly non-technical talk, but again, if you want to discuss some of the technical, find me at coffee, something. And I want to thank you for your attention, and I'm happy to take questions now.
Thanks a lot. Nice talk. Any question before the break? Here in the front row, please.
Yeah, a very nice talk, Marc. Not really a question, but more a comment on Verify. It's a very cool tool for the reasons that you mentioned, but I just want to highlight for everyone just to make sure that to avoid security issues. Verifpal is very good at finding bugs such as what you find in terms of protocol. However, unlike Tamarin Proverif, it cannot, for theoretical reason, completely prove a property because of some logic stuff. So you cannot really say Verifal proved that. You can say Verifal did not find any bug, but it's not as strong as a proof as Tamarin. And Nadim totally acknowledged that. But just in terms of marketing, you should not say, oh, it's proved because Verifal. No, it's very kind of verified.
Yeah, that's a great point. Thanks, JP, for the comments. And I believe this is why also I try to not say Verifal proved something. Yeah, it's a good point. Yes.
Any other question for Marc? Here.
Hi, Marc. Thank you for the talk. So you show some concrete examples of these formal verification tools used for standardized protocols or official libraries that implements them. But I wonder, since you talk about don't roll your own crypto, and you also work with blockchain where it's basically the wide west of everybody rolling their own crypto, why are they not used more in that space where even a simple key resharing algorithm could be at least at some level of security with a formal proof like this, with a tool?
Yeah, thanks for the question. Yeah, that's a good question. For these more sort of advanced primitives, this also probably should have been in my limitation list. The support there for more automated analysis is a bit harder because these haven't been sort of implemented in tools. We have, however, things like, for example, EasyCrypt that's trying to sort of capture universal compatibility, which is like a tool that's a framework that's typically used for protocols like TSS and these kind of things, which hopefully can start capturing these kind of things. But I think the short answer is that for sort of advanced things, we kind of stuck to pen and paper type analysis, which actually does happen, right? People do prove security of their zero knowledge things in some model, like algebraic group model or something. But we haven't really made much progress in terms of automating those things. But there are actually some interesting projects in terms of formal verification of, for example, ZKVM that are starting soon, which will be interesting to keep an eye on. Yeah.
Thank you.
Have time to take one last comment or question. Here again, Nico. Can you bring the mic to Linus? Here, thank you.
Yeah, here again. Thanks for the talk. So you talked about these verification tools for the actual protocols. Do you also use verification tools for the code? So you said you talked about code review, but you didn't talk about using formal verification in the code itself, which is also possible. But from what I saw and tried to play around with, is very hard and very difficult to actually get going. So I wonder whether you do that, and if so, what tools you use there.
Yeah, so formally verified implementation is not something that we're doing currently, but there are other teams out there that are doing that. For example, Crispin, which is a company that's actually worked on the PQXCH. Yeah, so I believe the answer to the question is that tools out there are available that you can use to sort of not maybe verify, but actually implement something that is verified sort of by nature. However, I believe that these use cases are kind of limited to specific things. I think lately there was a Google collaborative with Crispin to actually implement a sort of a verified post-quantum library. However, this might not be something that you might be wanting to use if you, I don't know, deploying some sort of new sort of basic protocol. So yeah, the tooling is there. Maybe the usability hasn't really sort of reached the level where you can just sort of start using that for any type of cryptographic application that you have in mind.
Thanks.
Thank you again.